Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to start a new topic under group properties of good properties of estimation. Properties of good estimation. So yesterday we already looked at unbiased estimator, and we also look at efficient estimator. So under efficient estimator, we know that when we have two estimator, so the estimator that have lowest variance is an efficient estimator. So let's say if we have more than two estimator, right? So we also don't know which estimator. So basically, we don't really know how many estimator are there in estimate to estimate the PDF, right? So let's say we want to know which is our estimator is having a lower variance or minimum variance compared to others estimator. So we're going to use a minimum variance estimator, minimum variance unbiased estimator, MVUE, right? Using the method of Kramer-Rao lower bound. Kramer-Rao lower bound. So given two estimator, theta 1 hat and theta 2 hat, both are unbiased estimator. So basically the first properties of estimator should be met, should be unbiased estimator of the parameter theta. And we know that in prior knowledge, efficiency, the best estimator is a smaller variance, right? The best estimator is the smaller variance. But the question is how good theta 1 and theta 2 hat to the theta n, the unbiased estimator of theta, parameter theta. And then we want to know, is there any other estimator? Is there any theta 3 hat or theta 4 hat or theta 5 hat and until n hat, right? So the question that we should answer, and that we need to answer is there a theta 3 hat that has a smaller variance compared to theta 1 hat and theta 2 hat? And then can we identify the unbiased estimator that having a smallest variance? Right, so this is the question that we need to answer by using minimum variance unbiased estimator using the method of Kramer-Rao lower bound. Right. So to answer the question, we need to use Kramer-Rao lower bound. Right. So if the variance of given theta hat is equal to the Kramer-Rao lower bound, so we know that that estimator is an optimal in the sense that there are no unbiased estimator can estimate a parameter theta greater precision, with a greater precision, right? So now look at theorem number 1. So let y1 until yn, right, be a random sample from a continuous probability density function fy theta, right? And where the fy theta has a continuous first order and the second order partial derivative at all but a finite set of points, means they have a value over there lah. And then suppose that ys for each probability of y given theta is not equal to 0, the probability is not equal to 0, right, does not depend on theta. And then let theta hat have probability of y1, y2 until yn be any unbiased estimator for theta, then the variance of theta hat should be more than or equal to negative n expected of second derivative of ln function PDF, right? So this is 1 over this function. So actually the function should be like this: 1 over negative n expected, so second derivative of ln of the PDF y theta, right, with respect to theta, So this is going to be the function of minimum variance unbiased estimator. So this is what we call as a Cramer-Rao lower bound. Cramer-Rao lower bound. Right. So look at theorem number 2. It's the same definition, right? So if you can see, for theorem number 1, we have two formula. Either we can use the first formula, this is the first formula, or the second formula should be variance of theta hat equal to 1 over n expected of derivative of ln fy theta, and then divide with respect to theta, and then we square this derivative, right? So this is going to be the second formula. So we can use either one, right? Either the first one formula or the second one formula. If the variance of theta hat is equal to this one, so then we can say that the theta hat is a efficient estimator for the parameter theta. So we need to know the variance of theta hat should be the variance of that the estimator. So if the variance is equal to this value, then it is an minimum variance unbiased estimator. Right? Are you clear with this one? So I just want to show you how to use Cramer-Rao inequality. Right? So if we have the variance of theta hat, right? The variance of estimated theta hat, let's say equal to something, right? Equal to, let's say, I just pick some value, let's say 2 power of alpha x bar, contoh, for example. So this value should be equal to either this one, either the first formula or the second formula. So if this value equal to the first formula or the second formula, then we can say that theta hat is the minimum, this estimator is the minimum variance unbiased estimator. Right, so this is an efficient estimator. Right, so now look at example number 1. So in example number 1, let me skip. Okay, right. In example number 1, we need to show that x bar is a minimum variance unbiased estimator of the mean mu for a normal population. Right. So we know that the PDF of normal population fx mu sigma is equal to 1 over 2 pi sigma squared. This is the square root. Exponential negative 1 over 2 x minus mu divided by sigma, and then squared. For x is between negative infinity to infinity. So this is the PDF of normal distribution. So if you want to find MVUE, the minimum variance of unbiased estimator, so the variance of mu hat should be equal to 1 over n e expected of derivative of ln fx, right, with respect to mu, and then we square this one. So I use the second formula. So you can use either formula, the first formula or the second formula. So for the first example, I use the second formula. Right. We know from the prior knowledge, so we know from prior knowledge, right? From prior knowledge, expected of mu hat, right, which is expected of x bar, should be equal to mu or summation of xi divided by n. So this is the first theorem in chapter number 1, if you can still remember, right? This is a theorem for sampling distribution. And then for variance of mu hat, it should be equal to the variance of x bar should be equal to sigma squared divided by n. So this is theorem number 1, chapter 1. So this is from prior knowledge. Right. So first step, we need to solve for the first parameter that we want to solve from this equation, which is ln fx. So ln fx, mu, and variance. Right. So this one should be ln 1 over 2 pi sigma squared, taking a square root, exponential negative 1 over 2 x minus mu divided by sigma squared. So far, are you clear with this one? Right? So this one should be ln 1 minus ln, this is a sigma only. This is the second part, right? I want to solve for this one first. Right? This one plus ln 2 pi power of half. So this is the second part. And then minus for the next value parameter, minus, because negative half ni letak kat depan, so 1 over 2 x minus mu divided by sigma squared. This is ln e. Right, that's why we got minus, right? So this one should be, this is equal to 0 and this is equal to 1, right? So this one should be negative ln sigma, and then this is minus ln 2 pi over 1 over 2. Actually, we can bring 1 over 2 in front, right? And then this is minus 1 over 2 x minus mu divided by sigma squared. Right, so this is the first part. We just solve the first one, right? So second step is we're going to solve for the second part, which is we're going to differentiate the ln fx with respect to mu, right? So this is d with respect to mu, and then this is negative ln sigma minus 1 over 2 ln 2 pi minus 1 over 2, this is, let's say we put bracket here, and then this is d mu x minus mu divided by sigma squared. Right, so next it should be with respect to mu, and then this one should be equal to 0. This is also equal to 0, right? There are no mu parameter inside the first part. So for the second part, we will get negative 1 over 2 sigma squared. We just take out the value of sigma over here, and then we differentiate x minus mu squared 2 minus 1, right? So this is going to be 2 and this is negative 1, right? So 2 dekat luar, negative dekat, this is differentiate of mu, right? So this one should be equal to x minus mu divided by sigma squared, right? You just eliminate the 2 here. Right. So this is also equal to x minus mu divided by sigma multiply with 1 over sigma, right? Okay. So now, sebab kita nak bagi dia nampak bentuk macam normal, standard normal distribution, right? When the standard normal distribution, standard normal distribution, where expected of x is equal to 0 and variance of x is equal to 1. Right. So the third step is, by looking at the formula of minimum variance of estimator, we will take the square of the derivative and take the expectation. Right. So we will take the square of derivative. This is the derivative. The square of derivative is 1 over sigma squared multiplied with expected of x minus mu divided by sigma and then u squared. Right. So from here, if you can notice, right, this value, right, if you can notice, this is expected of x minus mu squared over sigma squared, right? Which is also equal to 1 over sigma squared multiplied with expected of x minus mu squared, right? So we know that from the second moment about the mean, expected of x minus mu squared is equal to sigma squared, right? This is from second moment about the mean, right? So this one should be sigma squared, and then this one should be sigma squared multiplied with 1 over sigma squared. This one should be equal to 1. So then we will get 1 over sigma squared multiplied with 1. So this is equal to 1 over sigma squared. So the step number 4, by looking at the formula, we will need to 1 over n multiplied with expected value. So step number 4, it should be equal to 1 over n multiplied with 1 over square root sigma squared. So this one should be equal to sigma squared over n. So this value is equal to the variance of mu hat, should be equal to sigma squared over n. Right. So from the prior knowledge, we already know that the variance of mu hat is sigma squared over n. This is from sampling distribution theorem number 1. So since the variance of mu hat is equal to sigma squared over n, is also the Cramer-Rao lower bound equation also equal to sigma squared over n. So we can say that mu hat is minimum variance unbiased estimator. So far, do you understand the concept of minimum variance unbiased estimator? You can comment on the chat room. Do you understand? Or is there any question you want to ask? Can you comment on the chat room? Step number 3. So what is what's going on step number 3? Apa yang you tak faham? Kenapa? Okay, because sebab kita akan squarekan the expected value. If you look at the formula, the expected of kita squarekan the derivative of ln fx, right? Nampak tak? Square dekat sini. So that's why we square the expected of x minus mu divided by sigma. So you square, you will get this one. Are you okay? Kenapa over sigma je? Over sigma di mana? Because yang ini kita nak separate kan, kita tahu this one pun kita squarekan juga. So at step number 2, we get this one, right? Kalau kita squarekan this one, right? So we will get sigma power of 4, which is kita akan tak boleh nak cari expected dekat sini. So that's why we factorkan, right? X minus mu, this one sigma multiply with 1 over sigma. So from here kita nampak dekat sini, ini adalah mewakili standard normal distribution, right? So senang untuk kita buat step seterusnya. So kita nampak dia punya pattern, right? So kalau you tak nampak pattern dia, try to factor the equation. So baru you nampak pattern, then okay, you can proceed. Right. Second moment about the mean. This is a second moment about the mean, right? Sebab kalau kita guna expectation, kan, kita bawa sigma square dekat luar ni, right? So expectation of x minus mu squared is actually a second moment about the mean. Is actually equal to sigma squared, right? So when we solve this one, so we will get equal to 1. So senang lah, lagi senang untuk kita untuk solve the equation, alright? So ada soalan lagi? If you don't have question, then we can proceed with example number 2. Can we proceed on example number 2? Yeah, good. So now we look at example number 2. So suppose that the random variable x1 until xn denote the number of success, either 0 or 1. So this is going to be a binomial problem in each of n independent trial where p is equal to a success occur at any given trial. So is unknown parameter. Then this is the formula, the PDF, px p power of k 1 minus p 1 power of 1 minus k. So this is a Bernoulli distribution. So Bernoulli distribution. Soalan ni tak habis. Okay, let x is equal to x1 plus x2 plus until xn is equal to total number of success, and p hat is equal to x over n. And the question is, how does variance of p hat compare with Cramer-Rao lower bound for px P. Right? So here we want to know either P hat X divided by N is the minimum variance of unbiased estimator. So we have a Bernoulli distribution. So this is a Bernoulli distribution. Right. From a Bernoulli distribution, we know that the expected of X should be equal to P, and the variance of X should be equal to P multiplied with 1 minus P. Right? And for the unbiased, if we check for the unbiasedness, let's say check for unbiased, right? So expected value of P hat is equal to the expected value X divided by N. So this one should be equal to expected value of X over N. So this is equal to this is equal to P. This is actually equal to NP over N is equal to P, right? And for Bernoulli distribution, right, expected value of X is equal to NP, right? So this one should be equal to P. So now, yeah, I think this is a summation of X, right? So this is P, betul. Sebab Bernoulli mana ada N, right? This is expected of P, expected of X is equal to P, and then baru dia equal to P. So this is summation of N, summation of X, right? So I think something wrong with the question, right? Right. So now, let's say we want to estimate the variance of P hat. It should be equal to the variance of summation of X over N should be equal to 1 over N squared, the variance of X1 plus the variance of X2 plus until variance of Xn. Yeah, because we have an independent trial, right? So this one is equal to 1 over N squared. The variance of X is equal to 1 minus P. P 1 minus P. So this is going to be multiplied with N. So because we have several N variance X, so this one should be P 1 minus P divided by N. So this is the variance of P hat. Right? So now, since we already we already know that you see, yeah, I think the questions is tricky. So now they give us a Bernoulli distribution. We know that from a Bernoulli distribution, right? The expected of x is equal to p, and the variance of x is equal to p1 minus p. But in this statement, it says that it used n independent trial. So when n independent trial, it become a binomial distribution, right? So since a binomial distribution, but we still use the PDF of Bernoulli distribution. So now we start with the first one is taking a ln fx p. So this one should be ln p power of x, and then this is 1 minus p 1 minus x, right? So I tukar k dekat sini sebagai p lah, sepatutnya this is x, right? This is x. Okay. So next, this one should be equal to x ln p plus 1 minus x, right? Ln 1 minus p, right? So this one should be this one lah, tak boleh nak buat apa dah kan. So for the second step is we going to differentiate ln fx p with respect to p. So this one should be equal to x over p, right? So I letak betul-betul di notation dp x ln p plus 1 minus x d respect to p 1 minus p. So this one should be x divided by p plus 1 minus x, and this is going to be 1 over 1 minus p multiplied with -1. So this one should be x divided by p minus 1 minus x over 1 minus p. So this is for first derivative. Let's say I'm using the first formula in MVUE. Let's say I use the second derivative the second derivative of ln fx p with respect to p, right? So this one should be dp x over p minus dp 1 minus x over 1 minus p. So this one should be equal to negative x p negative 2. So I bawa ni ke atas, -1, so jadi -2. So this one should be with respect to, this is 1 minus x, right? So 1 minus p, this bawa ke atas, -2, and then this is -1 for the first derivative, dalam ni pula -1, right? So this one should be negative x over p squared minus 1 minus x divided by 1 minus p squared, right? So then number 4, I'm going to take the expected of the second derivative of ln fx p divided by with respect to p, right? So this one should be equal to the expected of negative x over p squared minus 1 minus x divided by 1 minus p squared, right? So this one should be equal to expected of x is equal to p, so this is negative p over p squared minus, and then this is 1 minus P over 1 minus P squared. So this one should be equal to, this is should be equal to negative 1 over P 1 over 1 minus P, right? So this is the value. So completing the formula, number 5. So Kramer-Rao lower bound formula, 1 over negative n expected of second derivative of ln fx with respect to P. So this one should be 1 over negative n, negative 1 over P1 minus P. So this one should be 1 over n P, kalau masuk dalam ni semua, n minus P. Sorry, this is not n minus P, but n dekat atas kan. This is 1, right? So this one should be P 1 minus P divided by n, right? So this is a lower Kramer-Rao lower bound. Kramer-Rao lower bound. Right, is equal to P 1 minus P divided by n. So we know that from the first equation yang kita dah buat tadi, this is the variance of P hat is equal to P 1 minus P divided by n. So this is equal to the variance, right? So this one is equal to variance of P hat, which is also equal to P1 minus P divided by n. So we can say that P hat is equal to, it is minimum variance unbiased estimator of P. All right. So this is going to be very long working. All right. So let's look at another example. So then we can understand the flow of finding minimum variance unbiased estimator. Right. So now look at example number 3. So show that the mean of moment, a random sample of size n from an exponential distribution population is minimum variance unbiased estimator for the parameter theta. So we know that from the PDF of exponential distribution, which is fx theta equal to 1 over theta exponential negative x over theta, right? So where x is more than 0, right? So from here, from prior knowledge, we know that the expected value of x is equal to theta and the variance of x is equal to theta squared, right? So soalan ni tak habis. We want to know the parameter of theta hat equal to summation of x over n is MVUE, right? So we want to know whether the parameter, the estimated theta hat equal to summation of x divided by n is the minimum variance of estimator of parameter theta. So the variance of theta hat, so now we need to find find the variance of theta hat. So the variance of theta hat is variance summation of x over n. So this one should be 1 over n squared, n multiply with theta squared. So this one should be equal to theta squared over n. So the variance of theta hat is equal to theta squared over n, right? So now let's do a minimum variance unbiased estimator formula. So I'm going to use the formula number 1, right? 1 over negative n expected of second derivative ln fx divided by with respect to theta. So this is quite easy formula. Formula number 1 is very easy to use. Right. So step number 1. Step number 1, we need to find a ln fx. So ln fx is ln with PDF is 1 over theta exponential negative x over theta. So this one should be equal to ln 1 minus ln theta for the first part. For the second part, kita bawa x over theta depan, x over theta ln exponential. So this one is equal to 0. Sorry, this one is equal to 1. And this one equal to 0. Right. So apa yang tinggal kat kita? Negative ln theta, right, minus x over theta. So this is the first part, right? The first part. The second part is we need to do two derivative, right? First derivative ln fx is equal to d theta negative ln theta minus d theta x over theta. Right, so this one should be equal to 1 over theta. This is minus. This is plus plus x over theta squared. Right. So this one should be equal to x over theta squared minus 1 over theta. Right. And then we're going to do for step number 3, second derivative of d ln fx. Right. So this one should be equal to negative 2x over theta power of 3 minus plus 1 over theta squared. Right, and then step number 4, we're going to take the expected of the second derivative. This is a second derivative, right? This is a second derivative of f ln fx with respect to theta. Right, ln fx with respect to theta. So this one, the expected of 1 over squared theta squared minus 2x over theta power of 3. Right, so this one should be equal to 1 over theta squared minus 2 over theta power of 3 exponential expected of x. So this one should be, the expected of x is theta, right? So this is 1 over theta squared minus 2 divided by theta squared. So this is negative 1 over theta squared. Right. So step number 5. Step number 5, we're going to take the 1 over negative n expected of the second derivative ln fx with respect to theta. Right? So this is the first formula that I use. This one should be 1 over negative n, negative 1 over theta squared. Right, so this is equal to 1 over n over theta squared equal theta squared over n. So the Kramer-Rao lower bound is equal to theta squared over n. And the variance of theta hat is also equal to theta squared over n. So this is based on the first determination yang kita dapat, the variance of theta hat equal to sigma theta squared over n. So we can say that since Kramer-Rao lower bound is equal to variance of theta hat equal to theta squared over n, so we can say theta hat is minimum variance unbiased estimator for theta. And theta hat is x bar, which is also equal to x over n. All right. Let's look at example number 4. Are you okay? Can we move to the example number 4? Right. Now look at example number 4. If y1 until yn is a random sample from a PDF 2y divided by theta squared, and the theta hat is equal to 3 over 2 y bar, right? So dia kata kat sini, the question is theta hat 3 over 2 y bar is unbiased estimator for the theta. Show that the variance of theta hat is less than Kramer-Rao lower bound for fy theta. So now we need to find the variance of theta hat. So first step, variance of theta hat is equal to the variance of 3 over 2 summation of y over n. So because y bar is a summation of y over n. So this is going to be 9 over 4. Right, 9 over 4 variance summation of y over n. So let's say I keluarkan n dekat situ. So this one should be 9 over 4n square, right? So this is summation of y, right? But the problem is for this distribution, we don't know the value of variance of y. The value of variance of y is the expected of y squared minus expected of y, and then we square, right? So we need to find the variance of y. So to find the variance of y, let me use green color, right? The expected of x is equal to integration from, this is from 0 to theta, x multiply with, so this is not x, this is y, right? Expected value of y, this is 2y divided by theta squared with respect to y. So this is going to be 2 theta squared over 3. And then the expected value of y squared is equal to integration from 0 to theta y squared 2y over theta power of 3, theta power of 2, right, with respect to y, and this one should be equal to theta squared over 2. And the variance of theta, the variance of y should be equal to the expected of y squared minus expected of y and then squared. So this one should be theta squared over 2 minus 2 theta squared over 3 and then we squared. So this one should be equal to theta squared over 18. Right. So we know that the variance is actually, we just input this one. So 9 over 4n squared multiply with n theta squared over 18. So this one should be equal to theta squared over 8n. So now we just discover the variance of theta hat, right? So then we use the, let's say I'm using the second formula of Kramer-Rao lower bound. So the second formula is 1 over n negative n multiply with expected of derivative of ln fy, and then with respect to theta, and then this is square, right? This is the second formula. So first step, determine the ln fy. So ln fy is ln, what is fy? 2y divided by theta squared. So this one should be ln 2y minus ln theta squared, or it become ln 2y minus 2 ln theta. So the second step is I'm going to take the derivative of ln fy with respect to theta. Tak kisah mana-mana formula pun nak pakai bersuka hati you. So I just tukar-tukar formula untuk you, right? So now I take the derivative of ln 2y minus derivative of 2 ln theta. This one should be equal to negative 2 over theta, right? And the third step is taking the expected of d ln fy with respect to theta. Right, so this one should be equal to because before that kita akan pakai the second formula, right? Second formula is we need to square the derivative, right? We need to square the derivative. So this is going to be square here. This is a big bracket. So this is going to be 4 over theta squared, the expected value. So the expected of 4 over theta squared, so this one should be the integration of from 0 to theta, right? 4 over theta squared multiply with the fx is 2y over theta squared with respect to y. So this one should be equal to 4 over theta squared again. Right? So then we will plug in this value into the formula, right? So step number 4, 1 over n multiply with 4 over theta squared. So this one should be equal to sorry, this is this is 4. So this is going to be theta squared over n 4n. 4n. Yeah. Kita bawa naik ke atas. This is 4n. So theta squared over 4n. So from here, Kramer-Rao lower bound is equal to theta squared over 4n. While the variance of theta hat is equal to theta square divided by 8n. So the variance is theta squared over 8n. So means Kramer-Rao lower bound is not equal to the variance of theta hat. So since this is not equal, so theta hat equal to 3 over 2 y bar is not MVUE, minimum variance unbiased estimator of theta. Right. This is how we do it lah. Okay. Buat ni pun dah penat kan? So I have another 2 example, right? So you want to see another two examples, example number 5 or and example number 6, or you want to stop now? You want to stop now, right? Okay. So I think if you want to stop now, it's okay. Don't worry. Just digest the formula and the theorem, right? So there is a tip to when to choose whether you want to choose the second formula or the first formula, right? So refer to theorem number 3. If the expected value of the first derivative of ln fx is equal to 0, and then we can use the first formula, right? If not equal to 0, then you can use the second formula. This is just a tip, right? So tip ni untuk apa? Untuk bagi senang you punya pengiraan, right? Kalau nak pilih mana-mana pun suka hati you, right? But this is just a tip. If the expected value of x, the first derivative is not equal to 0, then you should use the second formula, right? Second formula means you need to square the first derivative and there are no negative n, right? So just a reminder, this is the first formula. This is the first formula. Dalam kelas ni I sebut this is the first formula, right? And this is the second formula, right? Yang sama lah. So you can use either one, tapi this is just a tip. If the expected value is equal to 0, expected value of the first derivative equal to 0, then you can use the first formula. Untuk pengiraan tu dia jadi senang, right? Kalau it's not equal to 0, you can use the first formula. Ataupun suka hati you nak guna mana-mana, right? Another 2 example lebih kurang ke soalan yang kita buat di atas. Soalan dia lebih susah sikit lah. This is about, example number 5 is about gamma distribution. Right. Example number 5 is about gamma distribution. Right. So if you can see, this is a repeated example yang sama, just kita nak prove kan this is the minimum variance unbiased estimator. And then example number 6 is Poisson distribution. right? So I leave it for you, example number 5 and example number 6 as homework. You can try to do it, right? So if you can prove it, I'll give you the answer. Example number 5. Example number 5 is the minimum variance unbiased estimator. Example number 6 also minimum variance unbiased estimator. So dua-dua ni minimum variance unbiased estimator. So nanti you try buat, right? Bila you tak faham, you boleh tanya I lah, no worries, right? Tapi cuma assignment tu jangan tanya. It's your assignment, you kena buat sendiri. Try to Google, unless nanti lepas habis nanti baru I bagi tahu jawapan. Right, so don't forget you need to submit your assignment by tonight 11:59 PM, before 11:59, right? Dah settle, jangan lupa submit, right? Kalau tak submit, tak dapat markah lah, right? So before I end the session, if you have any question, you can raise the question now. Do you have any question?